I'm Paul Kovacs. I'm going to start today's session. Welcome to everybody who's here today. We've got several new faces, so welcome. Great to have you here. We've got about 50 people who are joining us electronically, so they're going to be listening through the microphone and watching the slides. We're going to try an experiment in June, Glenn. We're going to change our webinar format in June, where people who dial in are going to be able to ask questions and such, but our process here is please come and sit and talk directly with our guests. If people do want to view from the distance, we've been offering for a while the opportunity to just tune in and listen to what we're discussing, and I'm glad that we've got a lot of people tuning in today. But we're going to try in June having a more interactive process and see how that moves forward. Today we're going to talk about tornadoes. Just a quick reminder of a couple upcoming events. So on April 11, Dave Martell of the University of Toronto is going to talk about forest fire management. He's one of the leading modelers looking at wildfire risk in Canada. And Dave has been a regular participant in our workshops, but this will be his first time to present. So I hope people will be able to join us next month for the discussion with Dave Martell. And May 23, we've got Keith Thompson of Dalhousie coming in, and he's going to look at coastal flooding and some really creative tools that they have been pioneering, working at Dalhousie and working with Canada to try to look at elevation mapping, things like climate change and storm surge. Anyway, a couple of really interesting sessions coming up looking at wildfire and coastal flooding. But today, tornadoes. So welcome, David Sills. Great to have you here. Thanks today. David is with Environment Canada. We've had a chance to work together many times over the years, and David is a wonderful spokesperson about weather extremes in Canada, doing some real pioneering work in the area and recognized internationally amongst his peers as a leader in this field. And it's great for the first time to have you come and actually presenting to the group. Great, send it over to you.
Great, thanks, Paul. So on this first full day of spring, I'm going to shake off the winter. Thanks for coming out, and we're going to move into severe weather season and tornadoes. So I'm going to be talking, of course, about tornadoes in Canada specifically and how we're improving our understanding. I work in the Toronto office of Environment Canada, so this is Dufferin and Steeles area, and it's a cloud physics and severe weather research section. So just an outline of what we'll be talking about today, and I put it all in the forms of questions. We're going to answer some questions, and I'm going to tell you what the current status is, and then where we're going research-wise. So first of all, just what is a tornado? And yes, we're still moving forward on our understanding of that. How do tornadoes form? How are they rated? Where and when do they occur in Canada? How does Environment Canada provide tornado alerts? And lastly, in Canada, increasing in frequency and or intensity. So, what is a tornado? I'll start off with something kind of dry, just from our the AMS glossary of meteorology, and this is 2012. So, a violently rotating column of air in contact with the ground, dependent from a cumuliform cloud, one of those puffy white ones, or underneath a cumuliform cloud, and often but not always visible as a funnel cloud. Now, this is a definition that has changed recently. I found some inconsistencies in the definition in the glossary and asked for some changes, specifically one that makes sure that we include waterspouts in this definition and exclude things like gust devils and gustnadoes, which are little spin-ups that occur on the leading edge of a thunderstorm. So that was the definition as of 2012. Recently I looked again just to see if anything had changed, and of course it had changed. Now it's all inconsistent again. So that even the definition of a tornado keeps changing as people, we learn more and try to incorporate all we know into the little paragraph that describes this phenomenon. So a bit more about what a tornado is. So you might know that the winds in a tornado are actually going up into the cloud. And that's quite different than other types of wind that come out of the cloud. They start in the cloud and come down and spread out. So in this case, we've got wind that's spiraling in towards a really low pressure area in the storm, and then spiral upwards into the updraft region of the cloud. The wind speeds can generally go from 90 kilometers an hour up past 315 kilometers per hour. The average path, looking at our Canadian data, is about 250 meters, but you can see it ranges quite a bit, down to 2 meters. Sometimes you get a very tiny tornado that'll go in between houses. Other times you can have a very large tornado. I've had quite a few of these in the States recently, where it's 2+ kilometers wide. As far as path length, the average length is about 10 kilometers, but it can range quite widely again, from as low as 50 meters, just a brief tornado, to 100 kilometers or more. And this is just a picture of the Eli, Manitoba F5 tornado, the first F5 tornado recorded in Canada. Quite a beautiful looking tornado. Thankfully, it didn't cause much in the way of injuries or fatalities. There was, I think, one minor injury associated with this event, which was really something. And I've got a little video that I can show. Of the tornado, it was barely moving. This is an entire house was lifted off, and that's what gave it the F5 rating. Watch here as you see a van ejected. This is a minivan full of drywall, ejected from the tornado, flying through the air end over end, landing about 100 meters away. See all the debris in the air. They'd already gone through this area before, and then looped back around and came through again. And I think the only thing that prevented it from being a catastrophic event as far as people are concerned was that there was a big graduation ceremony going on in town, and everybody was off at the high school, I think it was, and nobody was home when all these homes were hit. So a bit of luck there. Turn to the presentation. So we'll go on to how do tornadoes form. So they can actually occur with any type of storm, and you might not be familiar with some of these types of storms. I'll try to describe them a bit. The supercell is kind of like the king of thunderstorms. It's the most organized, the most long-lived, strongest updraft, and those tend to produce the most violent and long-track tornadoes because they have that sustained, intense updraft. Other storms, more like lines of storms, called bow storms because they're bow-shaped, or squall lines. They can go hundreds of kilometers along a line. You can have little vertical vortices or little spins along the leading edge that the updraft of the storm stretches in the vertical and then intensifies. It's like when the skater brings in his or her arms and they start spinning faster, same kind of thing. Once that updraft stretches that vortex, then it's effectively bringing it closer towards its center and intensifying it. Pulse storms, just the storms you see in the summertime, they go up quickly, they go down quickly, but if they are strong enough and they happen to be over top of one of these vortices, they can stretch that vortex in the vertical again real quickly and produce a tornado, usually early on in the life cycle of the storm. But even what we call towering cumulus over the lakes, those big puffy white clouds over lakes, they can generate non-supercell waterspouts, we call them, something like this here. And you can get actually multiple waterspouts forming along this line of clouds. Yes?
I thought I'd heard out of some of the American discussion on the Gulf Coast that tornadoes can occur as a hurricane is unfolding, or spin out of a hurricane or something.
Well, you know, with a hurricane, there's spiral bands, and they can go quite far away from the center of the hurricane. And in those spiral bands, you have thunderstorms sometimes developing on, usually it's, I think, the northeast quadrant of the hurricane. So you have those thunderstorms, you have all this wind shear associated with the hurricane, and therefore you can get a tornado environment. And those tornadoes, because they're moving so fast, they can cause quite a bit of damage too. So the key with all of these different types of storms is you're trying to co-locate that enhanced vorticity or the enhanced rotation in the air with that strong localized updraft. So you might have an updraft over here and the spin over here. That's not going to help. But if they line up, that's when you can get the tornado developing. So we'll talk about the supercells first. So I told you that supercells are kind of like the kings of thunderstorms, and there's lots that occur here, but not all of them produce tornadoes. But the most significant tornadoes, and nearly all of our violent tornadoes, F4, F5 tornadoes, are supercell tornadoes. So they're the ones that generate the real big tornadoes that we see, especially in the United States. There are many supercell tornadogenesis or tornado development theories that have evolved through field work and modeling work over the years. It's still an active area of research, and I'll show some of that research in a bit. But back in the 1970s, Doppler radar, so that's the radar that can not only sense precipitation, but the velocity of the precipitation away and toward the radar, was used to identify this region of shear in a thunderstorm, which they call a tornado vortex signature. So they thought, well, we could see this rotation in the thunderstorm, and it happened 20 to 30 minutes before the tornado actually developed. And they could watch it descend on radar. So they thought, well, this is great. We've got a precursor to a tornado that we can monitor on radar, and that led to the installation of the Doppler radar networks across the U.S. and across Canada. So the hope was that these Doppler radar networks would rapidly advance tornado prediction. And they have to some extent, but it wasn't quite as simple as that. So here's kind of a schematic of a supercell thunderstorm. And what it looks like is the green area is precipitation. So you've got this kind of area of light precipitation that's heavier than heavier than heavier than hail in here, and this is where your tornado occurs. Back is the back end of the thunderstorm. So you've got updrafts coming in here, downdrafts coming back there, and this is, like as I said, this storm is it's so well organized that it can survive for hours like this. So this is the conceptual model from the 1970s of what a supercell thunderstorm was and where a tornado occurs. And it's a cascade process, they called it, where you've got a mid-level rotation, so mid-levels in the storm up and around 5 kilometers. That develops first. Then the rotation lowers to the lower part of the thunderstorm. Then you've got that tornado vortex signature, and then your tornado. So it seemed all nicely laid out. You've got something big aloft, and it comes down, and to a point for the tornado. And the high-resolution models at that time, which at that time weren't that high compared to today, but at that time, they appear to support this approach, this paradigm. So there was an experiment in the 90s called Vortex 1, and they thought that they'd go out there and make observations and just have to confirm all of this. And instead, what they found was that 70% of the significant supercell tornadoes didn't occur that way. They didn't occur the top-down way. They occurred in the bottom-up process. And what happens is you get surface boundaries, like cold air coming out from a thunderstorm, and that lays down a little boundary, kind of like a cold front. You've got cold air on one side, warm air on the other. So you've got several ways you can generate those kinds of boundaries. From thunderstorms, from our Great Lakes, you can have these boundaries moving in from the lakes with cool and marine air behind. Something called the dry line in Alberta and in the high plains of the U.S., and that's due to flow over the mountains. So you've got dry, warm air on one side, cool, moist air on the other side. So these boundaries are areas where thunderstorms can initiate and where there's a lot of rotation at the boundary, but the rotation is horizontal. And once the thunderstorm moves over that, it can tilt it up into the vertical, and that can give you the ingredients for producing a tornado. So now we've got a whole new way of looking at how tornadoes can form. And that was mid-90s. So this is not ancient history. This is all changing as we speak. That led to a whole bunch of questions that were unanswered from that first Vortex experiment. So there was a second one called Vortex 2. And that ran 2009 to 2010. It was a completely mobile experiment. There were over 100 scientists involved and over 50 mobile vehicles involved. And you can see the range of intercepts that we made while we were doing this project, all the way from South Texas up into Iowa and Nebraska. Quite a few intercepts of supercell storms, non-supercell storms, tornadoes, non-tornadoes, but there were quite a few tornadoes that were recorded. This is the instrument we brought out on this Jeep, and we were part of a larger group of similarly instrumented vehicles. And the idea was for us to get in the region of the tornado and make measurements on the ground with these mobile units. And you saw this picture in the beginning. This was during the project, and here's our Jeep, instrumented Jeep, looking down. We've got the tornado right down the end of the road, and all these vehicles saying, "Get me out of here." This is the storm, and you might not be able to see it, but there's a bunch of measurements made by the different vehicles around that thunderstorm. and they're all pointing inward toward that low pressure area. So they're all these are wind measurements, showing the wind wrapping in around that hook part, that the hook echo that comes around the supercell, and this is where all the rotation occurs, and the tornado was occurring right about there. So you can imagine it was kind of an intense field experiment to be a part of. There are quite a few graduate students involved in this, and that was good because we were in this area here, actually we're right there, and our role was to kind of monitor the situation out in front of the storm. Some of the grad students just liked the idea of going in behind into this region where there's white here, and that's where there was baseball to softball hail falling, and making measurements there. And they come out the other side, and their windshields be busted and everything else. But they were having the time of their lives, I'm sure. But we got lots of great data. The one tornado that's now become the most studied tornado in the world is from this experiment, the 5th of June 2009 in Goshen County. And you can see the tornado here. Laid over this is radar field. So this is toward picture, away from the picture. So we're able to lay the radar field right on top of the professionally done photography photogrammetry to get an idea of how the tornado, how it visually appears, how that compares to what the radar is telling us. These pictures were taken by a Doppler on wheels. So there's a radar on a truck. They get very close to the tornado and are able to measure these very fine structures in the tornado itself. So you can see here's that hook echo I was showing you before, but now you can see there's actually an eye in the middle of it. It's very similar to a hurricane-looking structure, but we're talking about something on the order of just a couple kilometers across, if that. And that's where the tornado was occurring. Here's the Doppler part of it showing that away towards signature where the rotation is occurring. Now after this, they brought all of that data and stuck it into a numerical model, and now we're able to do things like looking at how the wind field is all around that vortex in the center, and also looking at how air parcels move through the storm. So this is how we're finding out how the tornadoes actually are forming, which is still not exactly a solved problem. This is just another example of this numerical modeling that's going on, and the different colors here. Well, the green is the storm itself. The purple is the rotation in the thunderstorm and how it lowers and develops rotation near the surface where you get the tornado coming from. So you can see we're getting closer and closer to be able to see exactly what's happening inside that storm. Now, I mentioned supercell tornadoes. Move on to bow echo tornadoes. As I said, a bow echo is a thunderstorm that's kind of a bow-shaped. Usually it's bowed because there's strong winds coming in behind it. These are likely prodigious tornado producers. We do know that about maybe 40–50% of our tornadoes each year come from these kinds of storms. Unlike supercells, the tornadoes actually form out ahead of the thunderstorm. Here's a little example here where you can barely see that tornado up in the front of the thunderstorm in the updraft region, and there's all the wind and rain coming in behind. So because of that, many of the tornadoes go undetected. They're really hard to capture. They happen quickly. Sometimes they're actually wrapped up in rain, so no one can see them. So we're hoping we might get more photographs of these kinds of things now that cell phone cameras are so widespread, and we'll get a better idea of when and where these happen. This is how that bow echo develops. So you start out with this kind of straight radar echo, and then you can see there's strong wind coming through the center of it, and it turns it into more of a bow shape. When that strong wind comes through and starts reaching the surface, that's when you get your tornado. So here's another look at it here. There's your bow-shaped echo, the tornado out front of the storm, and this is the side view where that jet of air comes from aloft, and when it reaches the ground, and there's an interface between the updraft air and the downdraft air, that's where you get your tornado developing. And then the last one is something called Landspout tornadoes, and we call them Landspouts because the formation process, the appearance is similar to waterspouts, but they're occurring over land. These tend to be more of the weak tornadoes that occur with those kind of the puffy white cumulus that you see going up on a summer day. They don't last very long typically, and they're fairly weak. They commonly appear thin and rope-like. Here's an example here where it almost looks more like a dust devil than a tornado. They occasionally occur with atypical translation motion. So a lot of the tornadoes with bull echoes or with supercells, they go with the storm, which is often from the west or from the southwest. With these, since usually they're not occurring with a lot of big flow aloft or anything like that, they kind of go in the direction that the boundary that they form on is aligned with. So say there's a lake breeze north of Toronto, lake breeze front, and the front goes from, say, the airport off into Buttonville area. What will happen is a thunderstorm will initiate on that boundary, that kind of little cold front, and when it does, it can move along that boundary and sometimes back towards the southwest and produce a tornado as it does. And that's something that actually happened. That was the 1984 King Coil tornado that moved through the Toronto area along a lake breeze front. So that's what's unusual about these is they can move in directions other than the normal from the southwest or from the west. And this is how those ones form. So we've got something like a lake breeze where we've got cool air, and there's this boundary between that cool air and the warmer air ahead of it. And then there's wind along those two, and the wind might be in different directions. And because the wind's in different directions, you get little spins starting because of that shear in between the two air masses. So you can see these little areas of spin that form right along the leading edge. And it's not just spin, but lift. So you can see clouds starting to form along these two. So they start to kind of group together, and you get stronger and stronger vortices along that leading edge, and they lead to stronger thunderstorms. And they're developing right over where that rotation is. So as the thunderstorm matures and the updraft is very strong, again, it stretches that vortex in the vertical, and then the rotation becomes strong enough to be a tornado. And that's what we have going on here. And then as the thunderstorm dies out, the cold air from this side of the boundary wraps around and cuts off the tornado's updraft, and the tornado kind of falls apart. Now, waterspouts, any of the processes that we mentioned before can occur over water. And so with a tornado occurring over water, we just call it a waterspout. But it's basically the same thing. It's a tornado that can occur by any of those different processes. Okay, so let's move on to how we rate tornadoes. So you might know Environment Canada conducts on-site storm investigations. I've done dozens and dozens of them. But, and here's an example of the Goderich tornado and us doing the damage survey for that. Sometimes if the site is too remote or we're getting lots of pictures in and we don't really need to go out to see, we just do a remote survey, use all the data that we've collected, and base our decisions on that. But the goal of the survey is to identify various parameters related to the event. So first of all, was it a tornado? A lot of wind damage is caused by stuff other than tornadoes, the wind coming out of the thunderstorm, the downburst or microbursts, or just straight line winds. So we have certain things we look for to know if it's a tornado or not. Basically, a long, narrow path is the main thing we're looking for. So you don't get that with microbursts or straight line winds. What was the intensity of the event? And we'll go into how we measure the intensity in a second. When did it occur? Where did it occur? The injuries and fatalities, any property damage, all these things need to be answered so we can enter all this information in the database and build this better picture. So how we rate tornadoes up until 2013 was using the Fujita Scale. And this is developed by Ted Fujita, University of Chicago in the 60s. And he made a good guess at what level of wind would be required to do what level of damage, and called it F0 through F5. So F0 being the weakest, F5 being the strongest. And it was based on a limited number of damage indicators, mostly a residential home. It can be used for tornadic and non-tornadic wind damage, but mostly it's applied to tornado damage. And that system of measuring the intensity of a thunderstorm was implemented in the U.S. and Canada in the 1970s, and we've been using it up until just recently. But there were recognized problems with that system, mainly that the wind speeds associated with the various levels of damage were far too high on the high end and too low on the low end. So an effort was made to come up with an improved Fujita scale, and they call that the Enhanced Fujita Scale. So this was developed down at Texas Tech, and there were many U.S. interests involved in this. So the idea was to improve the wind speed, wind damage correlation, and have a larger number of damage indicators, but also keep it consistent with the existing U.S. database so that you can use all of it together to look at how things have changed over time. So this was adopted for use in the U.S. in 2007. It took a while, but I finally got it adopted as Environment Canada in 2013. And the first tornado in Canada rated with the EF scale was April 18, 2013, Shelburne, Ontario, rated EF1. And I'll be showing an example of that particular tornado in a bit. So here's how it works. The EF scale is made up of a number of damage indicators. In the U.S., they have 28 damage indicators. And they include farms and residences, commercial and retail structures, schools, professional buildings, metal buildings and canopies, towers and poles. And then there are a number of different DIs that we have added, we just call them the Canadian DIs, because they were missing from the American list, or we knew there were problems, and sometimes the Americans know there are problems, and we've gone ahead and made changes to one of the DIs to rectify those problems. The problem is in the States, right now, there's no process to change any of this stuff. No one actually owns the EF scale. So when we implemented this in 2013, we wanted to kind of jump ahead, learn from a lot of the mistakes and problems that they've dealt with, and advance it. So that's why we have some new and revised damage indicators for our implementation of the EF scale. So for each of those damage indicators, you have degrees of damage. So here's a damage indicator: small barns or farm outbuildings. Gives you an idea what the typical construction is, and then you have the degree of damage levels. So at the first level is threshold of visible damage, and then it goes all the way to total destruction of the building. What these are the wind speeds in kilometers per hour expected for that kind of damage, the lower bound and the upper bound. So it gives it a bit of a range, a bit of flexibility in assigning a wind speed to that. Once you have the wind speed, then you can say whether it was EF0 through to EF5. So though the F scale and EF scale wind speeds are different, they both have the same damage scale. So the ratings based on damage for the older events will match the ratings for the new events. For instance, the old F2, in order to get F2, you'd have to have a roof removed from a house. And with the new EF scale, EF2, again, you need the roof removed from the house. So the damage stays the same, it's just the wind speeds associated with that damage that have changed. And this is just a comparison of the EF winds and the F winds. So here you have the F or EF number going from 0 to 5 at the bottom, and then wind speed along the side. And the orange and purple are where the upper and lower bound of the EF scale, and here is the F scale here. So you can see at the upper end, we've lowered the wind speeds quite a bit. At the lower end, we've brought them up. One other thing we wanted to change for the Canadian implementation is the lower bound of wind speed. What they did, they had a process where experts from meteorology, from engineering, from architecture, and so on, got together and came up with wind speeds associated with each type of damage. And that's what all these data points are. So once they got all these data points for all the different damage indicators, all the different types of damage, all the DODs, it ended up on here. And what they did is ran a linear regression line through it and said, okay, this is how we're going to use this equation to go from the F scale to the EF scale. And when they did that, the lower bound of EF0 ended up being 65 miles per hour. Now, wind warnings in Canada, United States, and severe thunderstorms in Canada, United States, they both say that wind damage will begin at about 90 kilometers per hour. 65 miles per hour is 105 kilometers per hour. So there's this 15 kilometer an hour gap where you could have damage but you couldn't officially call it a tornado. So we had a problem with this, and I think some of the Americans do too, and tried to find a way to bring that lower end down so we can make it consistent with our other warnings and make sure that when damage occurs, you can call it EF0. So what we did is just take the same data that we started with and just applied a power law curve rather than the linear regression curve. And that kind of changes everything in a good way. It keeps everything nearly the same here, but it lowers it at the low end. And suddenly you've got the lower bound of EF0 becoming 90 kilometers an hour. So it worked out well, and that's what we decided to implement. So based on that, this is what our winds are associated with the EF scale. So EF0, 90 to 130 kilometers an hour, and you can see how the winds creep up with each level, up to 315 or more with EF5. Any questions on any of that? No? Good. Oh, and I guess this is what the old wind speeds are here. So you can see, again, how the wind speeds have come up at the low end and significantly come down at the high end. So it used to be the high end was up to 510 kilometers per hour, and now we've gone down 315 or more. So we are trying to develop an EF scale standard so that changes can be made officially to the EF scale. There's a team that I'm part of that's working on that. I'm working on getting a standard to be administered by the American Society of Civil Engineers. And the revisions that we made in Canada are going to be considered as possibilities for this final standard that's going to be adopted. And then once the standard is adopted, then we're hoping to have a yearly process where people can submit proposals for changes, and then there's an official process to accept those changes. Yeah.
The Americans have switched over, and we've switched over. Are there other countries around the world that are using the newer scale?
Good question. In France, there's a group that has adopted it, and it's not clear how they do it over there. There's a group that does kind of tornado rating on their own outside of the government, but the government itself hasn't adopted it, and none of the EU has adopted it. Just lately they've issued a statement saying they think it needs more work. So, and the problem is that the building standards in North America are in some places quite different than in Europe. So they're wary of bringing that building standard, the EF scale, basically scaled to that standard over to Europe. But I think there's going to be events especially once it gets into the ASCE and becomes a standard, and there's a way to make changes in the future. I think it'll eventually spread globally, I think.
It's my understanding in terms of the frequency of tornadoes that the Americans have the most in the world, that we're sort of second?
Yeah. There's the Brits like to say that they're second because they get more tornadoes per square kilometer than we do in Canada. But as far as sheer numbers, we're second after the Americans.
So it may be another reason why other countries haven't turned to this, because they just don't have a lot of tornadoes.
It's true. Yeah, it's not quite as much of a problem in other countries.
Is there something about North America that leads tornadoes that why wouldn't Russia want to think about tornadoes happening?
Well, there's a certain set of conditions that you need for the kind of tornadoes you see, especially in the States. And what they've got there that's special is you've got the Rockies on the west, and then the Gulf moisture coming up from the south. When the air moves over those Rockies, it really dries out, and it ends up over top of that moist air, and that sets up the perfect profile in the atmosphere for the development of really strong thunderstorms and supercell thunderstorms in particular. And so that's why they have such a problem with tornadoes through the Great Plains area, and then gets into the south as well. We have our own setups in Ontario. In Ontario, we've got the Great Lakes, and I'll show that in a bit, how it can either suppress thunderstorms or enhance thunderstorms. So there's some meteorology that goes on that enhances our tornado track here. And out Alberta way, it's completely different. All the moisture there doesn't come from the Gulf. It comes from evapotranspiration of the wheat crop, and the moisture moves from areas toward the mountains in Alberta sets up a dry line, as I mentioned before, with the air coming over the Rockies, and that's how they get their severe thunderstorms. So yeah, it's different in different parts of the world, but definitely that setup in the States with the Rockies and the Gulf being right there. There's only a couple places in the world that have that kind of setup. One of them is Bangladesh. They get huge tornadoes in Bangladesh, and because there's not a lot of infrastructure, it causes a lot of fatalities. But not, I don't know anywhere in Russia that would have that kind of setup. So there are favored regions across the globe for sure. Okay, and I mentioned that there will be proposals for changes that will end up coming in for the EF scale, and guys like Greg Koch and Ori Hangen at University of Western Ontario are doing the kind of work that will end up resulting in changes to the EF scale in the future. Greg's team is working on how trees, how vehicles interact with wind, and how that, and buildings too, and how that might be written up as a change to the EF scale. And then if you don't know about the Windy Dome, this is a new tornado and downburst simulator that was built in the London area and can create a tornado inside the building. And they're planning to do all kinds of studies with that on how the winds correlate to damage. Okay, so now on to where and when do tornadoes occur. This is the earliest attempt to map out tornado occurrence in Canada, and this is by Mike Newark. This is back in 1984. So this is an Environment Canada employee who took an interest in tornadoes, started collecting data from mainly Ontario and then spread out over the entire country of Canada, and came up with this early climatology. And so he's got the really busy areas for tornadoes down in southwestern Ontario, of course, and parts of the southern prairies. But everywhere there's these dotted lines, he didn't have enough data to really do much and just kind of extrapolate it. So the maximum frequency that he came up with is 2 tornadoes per 10,000 kilometers per year. That was down in the Windsor area. And I don't think anywhere in the prairies got that high. The next attempt was by Dave Etkin and his co-authors back in 2001. So again, taking the data set, and he divided it up into 0.5 by 0.5 degree grid cells, and came up with where tornadoes occur most often. And his method resulted in a maximum frequency of 7 to 9 tornadoes per 10,000 kilometers squared. And that's getting more into the kind of numbers you see in the high plains of the States, in Oklahoma, and that kind of thing. Of course, that's only in a few spots. Most of it's in the kind of 2 to 3 range. But again, what we're seeing here is in the populated areas, you can see that we're getting these high numbers. In areas that we know that get severe thunderstorms but don't have a lot of population, you basically got nothing. So that's one of the things we wanted to work on when we worked on this next project. So I'll just give you a bit of backstory on this project we've been working on for the last several years to build a new Canadian tornado database. Tornado resilience measures were written into the National Building Code in '95 based on a study of the Barrie and Grand Valley F4 tornadoes back in 1985. So first of all, it took 10 years for this forensic study to be done. And it took another almost 20 years for us to actually be able to implement this stuff. But so these measures included anchors in manufacturing permanent structures and masonry ties in permanent structures, such as schools, hospitals, and auditoriums. So these are relatively inexpensive measures to undertake, especially for new buildings. But the implementation of this in the building code required a clear definition of tornado-prone regions of Canada. And those measures sat in the building code unactivated since '95 because Environment Canada never did come up with these tornado-prone areas. So we finally had the confidence in the database and the resources to do this in the last several years. And so we undertook this multidisciplinary research initiative within Environment Canada. You can see the number of people involved here from across the country. And what we wanted to do was build an updated 30-year national database. So the first database by Mike Newark was 1950 1979, so 30 years. So this is an update, 1980 to 2009. Some of the problems were that each of the regions across Canada, and there are 5 different regions, they all have their own databases, their own ways of doing things. So all of this needs to be merged, and any inconsistencies need to be addressed. We tried to use this Tornadoes and Ontario project approach. This is the approach we took with the Ontario data set that tried to make it all more consistent, and that's what we applied to the entire database. But the other thing we needed to do was find a way of filling in those gaps in the data, the underreporting in the rural and remote areas. So before I get into how we did that, I'll just give you some idea of what the observed database was telling us. So this is all based on verified tornadoes from that database. And this is a 30-year average annual tornado incidence across Canada. So nationally, on average, we get about 52 tornadoes per year. That's verified. So reported and then verified. And we know there's a lot more going on than that. But how it breaks down across the country is most of the tornadoes occur in the middle of the country. So you've got 18 tornadoes per year here in Saskatchewan, as opposed to British Columbia, which is not even 1, and combining all the Atlantic provinces, it's 1.2. Here in Ontario, it's more like a dozen tornadoes every year. But there is quite a bit of seasonal variation in this. This is tornadoes by month, and also showing what the F scale is here. So you can see the tornado season ramps up late spring, peaks in July, and then kind of peters out in the fall. And looking at the F scale colors here, you can see that the vast majority of these tornadoes are weak. F0, F1 tornadoes. Anything green or higher here is where we get into the stronger tornadoes. And you can see that there's really not a lot that occurs compared to the large database. And this is not just Canada. This is the same kind of stats you get in the United States. Most of them are the weaker variety. Here's tornadoes by local time. You can see again, the peak is 4 o'clock and 7 o'clock. So that's when you've got the most daytime heating available, the most instability in the atmosphere. So that's when you're going to get the big storms with the strong updrafts. That's where you're going to get your big tornadoes. So 85% of the tornadoes occur between 1 and 8 p.m. They can occur overnight. They just don't do it very often. You need special circumstances in order to do that. So some other stats from this 30-year period. There have been several notable events. Of course, the Barrie tornadoes in 85, the Edmonton tornado 87 F4, Eli from 2007, and then we've had a couple of events lately where we've had a large number of tornadoes in one event. So this was 2009 in Southern Ontario, 18 tornadoes in one event, ranging from F0 to F2. And looking at the data, we see the average path length is again about 10 kilometers, average path width about 250, the average number of fatalities per year, 2, and the average number of injuries per year is 29. But those are biased by large events. So we tend to have events occasionally where we've got a lot of injuries and maybe tens of fatalities, and then long stretches where we don't get anything. So those averages are a little misleading in that respect. Well, we can go many years without seeing any injuries or fatalities. So here's what it looks like when it's all mapped out. The color coding now is F0 to F5. So here's your big Eli tornado, big black spot. Our only F5 in the country that we verified. And you can see there's been F4s down in Southern Ontario, down in the prairies, but when you get down to the F1s and F0s, they've pretty much occurred all over the country. But again, you see there's quite a few areas where it doesn't look like much is happening, but meteorologists know and forecasters know that there are big storms there, and there should be tornadoes happening somewhere. So what we wanted to do was come up with a way to fill in those gaps. And the idea I had was, well, we've got a new data set that no one has had before in the past, and that's our lightning data set. So this is the Canadian Lightning Detection Network. We've had data since 1999. So this is a 10-year data set here with millions of flashes, so very robust data set. And that's really showing us where thunderstorms are occurring most often. And we know that in order to get a tornado, most of the time we have to have a thunderstorm. So this is going to give us an idea of where tornadoes are occurring, but we're not picking them up. Okay, and you can see in those regions that I showed where we don't have a lot of tornado reports, there's still quite a bit of lightning activity, thunderstorm activity. So we had a grad student from U of T that was working with us, and he wanted to apply the latest ideas in Bayesian statistical modeling, and so that's what we did. And we used the CLDN lightning flash density climatology to model the tornado incidence, and we used population density as a mask to adjust for the population bias. So what that means is in high population areas where we can assume that most of the tornadoes are seen, we just use the observed tornado count. But otherwise, the true tornado count is modeled using that lightning flash density as a predictor and weighted by population density. So here are all the observed tornadoes applied to a 50-kilometer grid. So we can do the math on the grid. Here is the population density weighting math. Basically, anywhere that's black, we're just going to use the straight counts. We're not going to weight it by population at all. But as you get into more gray and white areas, I'm going to apply more and more of a weighting to the lightning data. And here's what the result is. So suddenly we've got tornado activity happening in these areas that we have no observations for, and in here as well. And interestingly, this area in here, northeast of Lake Superior, really didn't get filled in. And we're thinking that might just be because Lake Superior is so big and cold, it just shuts off everything to the northeast of it. So there really is a hole there. But in this part of northwestern Ontario, the northern prairies, this part of Quebec and northeastern Ontario, the numbers did come up. The maximum frequencies are matching what Efkin had seen with 7 to 9 tornadoes per 10,000 kilometers squared. And there's that area I said that we had little in the way of reports. And we've gone from 62 tornadoes per year to 230 across Canada. So it's a large increase in the number of tornadoes that are occurring. And I don't doubt it for a minute. It's a large landmass, lots of thunderstorms happening, and there's just many tornadoes that we're not seeing. Again, a lot of them are going to be weak F0, F1 tornadoes, but they're tornadoes we're not getting reported. So we've got, go back for a second. So we've got all these tornadoes that we've got modeled, but we wanted to know what parts of the country are prone to strong tornadoes, so F2 and greater tornadoes. So how do we do that? Well, we found a paper from Harold Brooks and Chuck Doswell in the U.S., and they look at tornado data and say, well, we know fairly well about the strong tornadoes in the U.S. And so if we come up with a slope on a log linear graph from F2 to F4, that will give us this line that should be able to show us where we should be with F0 and F1 tornadoes. And what they use this for is checking the data quality of tornado data sets around the world. Since this F2 to F4 slope is usually robust, they can project that out over here and then see how far the line falls for F0 and F1, and that gives them an idea of all the tornadoes are missing, basically. And as the tornado data sets have been improving, that line has been going up and up. We've seen that in Ontario as well. But what we're going to use this for is use the F2 to F4 slope in Canada to be able to predict how many of the total tornadoes we've modeled across Canada fall into each of these bins. So we're partitioning the total using this slope. And when we do that, we get different categories. So we've got prone to significant tornadoes. So this is the probability of an F2 to F5 tornado estimated to exceed 10 to the minus 5th kilometers square per year, which is an engineering threshold. The F0 to F1 tornadoes will be more frequent. The second category is prone to tornadoes, but just of the F0 to F1 variety. And then another category where tornadoes are observed, but rare. So it falls below 10 to the minus 5th. And this is what the map looks like when you apply that. So what this is telling us is that these areas in dark gray are prone to significant tornadoes, F2 and up. So anywhere in those areas could possibly see an F5 tornado. In these other areas in the light gray, it's much more likely to get an F0 to F1 tornado. An F5 tornado would be very unlikely there. And in these areas back here, a tornado is fairly rare in general. And that's the map that appears now in the building code. Now we wanted to check this against all the tornadoes that we have. So this is going back to 1792, the first tornado down in the Niagara area. The data quality isn't great as you go back as far as, we know we're missing a whole bunch of data, but these are all the points that we do have. So how does this fit into what we modeled? And you can see that anything green or higher is a strong tornado, and they fit fairly well within that dark gray area. So we know we've mapped this pretty well.
Where's that dark gray area right at the end there?
This one here?
Yeah.
Yeah, interior British Columbia. Yeah, so it's like the Prince George area. There's a kind of a flatland in there that I guess there's just enough space for thunderstorms to get going before they hit the Rockies. So that surprised me as well. There's this little max out in British Columbia where they can get, again, strong tornadoes. Now that grad student I was mentioning, Vincent Cheng, he's gone on and redid the analysis using a 25-kilometer grid just to try to get more accuracy. And this is just tornadoes. He didn't look at strength of tornadoes, just the tornadoes in general and where they occur in Canada. This was recently published in the Journal of Climate. And it gives you a really good idea where our most active tornado regions are. So it's in this corridor, Windsor to Barrie, and southern prairies especially. Southern Saskatchewan turns out to be probably the biggest hotspot for tornadoes in all of Canada.
When you go from observed and verified tornadoes to model tornadoes, it's a very big change in the count, mainly with the small tornadoes in that particular area. What's the state of the American research on the same question of observed versus model? And a related question, but different. If you took the American analysis, in particular at the northern part of the U.S., northern part of the prairies, and put that next to this analysis, I remember seeing some seismic analysis, and you put the American and the Canadian, and in some cases it fit really well, in some cases it did not.
Right.
The West actually, in the earthquake, fit well, and the East didn't fit very well. Anyway, to what extent does the American research show that this is a natural extension of what
Sure.
we're looking at?
Okay. Well, number one, the Americans haven't tried using this lightning approach. And I think it makes a big difference. One of the reasons that makes a big difference is because if you try to bring up the tornado count using just population, areas like this, you're not going to see much change. There's not much population out there. And that's what a lot of different American groups have done, is use population somehow to try to bring those numbers up. It works well in populated areas or near populated areas, but where there's no population at all, it's not going to help very much. It's a non-meteorological variable, so you're going to get unphysical results a lot of the time. When you're just looking at straight observations, it matches very well. So we know we're, observation-wise, you're doing fairly well at catching what they're catching. But when you start looking at tornado incidents, the best estimate of tornado incidents in the U.S. comparing it to this, there is a huge step there. And I really want to, the next step for this is apply it to we've got the data for all of U.S. and Canada. And I think the Americans are going to be very surprised, because we know that our hotspot is in the southern prairies here, even just looking at the ops, right? But if you look at the American occurrence maps, it tails off about here. So I don't think they've got a great idea what's going on along the border here. And I think this research is showing them that they got to take a second look at their northern states.
A related question. I think we saw there from a moment ago, but so you took a block of time that was done in previous analysis, I forget how many years, and then a new block of time, 30 new years that you brought in. To what extent have you tried to look to see if there's any change taking place over time? Are the data rich enough, and have you done
between the two 30-year blocks?
Are the zones of risk in any sense?
We haven't done that yet. That's something we need to do. I do know that the data set that Mike Newer put together has had some problems in some of the tornadoes were actually not tornadoes. They're probably more microbursts. There wasn't a lot known about that at the time that he was doing that work. So the data set from 1980 on is probably a lot more accurate in terms of this is really a tornado. But I think it is worth looking at, though, comparing the two data sets. And we have also just taken that data set, the new data set, and added all the stuff that we have from the previous years to try to get a better idea of the entire, from 1792 on. But as I said, it's really patchy. In some regions, they only started recording tornado data in the last 30 years or so. So in Ontario, we've got a pretty rich data set. And in the prairies, it's okay, but in places where they don't occur as much, they haven't paid nearly as much attention to it, and therefore the quality of the database isn't that great.
I'm really interested in this little inset in the top right corner.
Yeah.
Like that would imply, a more severe risk in Caledon, for example, than London, Ontario.
Yeah.
Right? And I'm wondering, do you think that's legitimate? I mean, to drive the data you've got to that level of resolution, or do you think there's something there, like maybe the Niagara escarpment, that's contributing to this? I don't know. Grasping.
No, it's a great question. There are two areas on here that are bullseyes. I guess this one here and this one down here. This in Windsor is actually an extension of the American max. It manages, in a lot of cases, the storms that are in Michigan manage to get across the border and cause a tornado before they hit the Great Lakes area. And that's what's happening here. Is the Great Lakes are having a huge impact on where tornadoes occur. Because it's cool marine air, it suppresses thunderstorms. And I'll show a graphic a little later to give you the real detail. You can see it in the tornado occurrences. So it kind of shuts down the tornado activity, not completely, as you can see, but it shuts down kind of stronger stuff in the London area. There hasn't been a major tornado through London. And it's a kind of a sprawling area, so you think by now we'd have seen something go through there. But in here is where you see the lake air start to have less influence, and also the lake breeze fronts themselves, as I mentioned, can be sources for the initiation of thunderstorms, and the vorticity in those boundaries can also provide the rotation for tornadoes. And that's what we see up here, is that the Lake Erie Lake breeze front, the Lake Huron Lake breeze front, in these southwesterly flow situations can go way inland and interact up in this area, and that's why we're seeing that bullseye up there. So I think it's perfectly in line with other things we've seen. I've been studying the lake breeze effect on thunderstorms since the mid-90s, and heavy rain events, lightning, tornadoes, it all says the same kind of thing. That you've got this bullseye region in this area here.
Well, one other thing that I don't know if it's happened in your research, but tends to happen, is that tornadoes don't get counted over water.
Right.
It's over land.
Yeah.
So if you're aggregating regionally, you're going to get an artificially low count on the shoreline because you're only counting towards one side as opposed to the other.
Yeah. Well, we count waterspouts that make landfall. So those are in there. The ones that are strictly over the water is in another database, Waterspout database. And we haven't merged the two yet because the quality of that database doesn't match the quality of this database, but we're working on it.
But what you're seeing here is that the frequency is getting less as you get to the coast, which would lead you to suspect there might be some discrepancy in how they're counting and aggregated there.
I'll show you a figure in a minute that'll convince you. Okay.
Have you looked at other things besides lightning data to kind of enhance the database, like Cape Shear or meteorological parameters such as those?
You mean as far as the modeling goes?
Yeah, so instead of using lightning to enhance it, have you thought about other things?
Thought about it, haven't done it though. Yeah, I mean that's one thing that other groups have done is use things like Cape and Shear. Cape and Shear, for those who don't know, it's the amount of instability and the amount of direction and wind change, wind change with height. And you need both of those to get a severe thunderstorm with some other stuff, but those are the main ingredients. So if you look at past data sets from like reanalysis data sets that have those variables in them, you can map out where supercell tornadoes are going to be more likely. The problem is that I'd say about half of our tornadoes are not supercell tornadoes. They're these Landspout tornadoes or bow echo tornadoes, and they're really hard to pick out with the Cape Shear kind of approach.
How do you collect the lightning flash information?
Oh, okay. Yeah, there's lightning sensors all over the country. I think there's 80 in Canada, and there's a lot more in the States. And so all the data are picked up by these sensors, sent down to Tucson, Arizona, I think it is, where Visela company runs the data collection center, and then sends out data packages for the forecasters and for our research. But yeah.
In the spirit of the same question, about besides using lightning, Doppler radar is something that's been now in place for a while, and Doppler radar is looking over. Does Doppler radar suggest that this map is a more accurate depiction?
Doppler is tough because it doesn't actually show where a tornado is occurring. The tornado is just too small. We've had tornadoes occur within 100 meters of the radar, just couldn't see it. What it does show you, and I mentioned at the beginning of the presentation, was that it's the conditions that lead to a tornado. And usually that's a larger scale rotation in the thunderstorm aloft. So it's pretty easy for the radar to pick that up. So we have done climatologies of that kind of mid-level rotation, and it does show the same kind of, at least in this area here, it does show the same kind of things. But across the country, the radar coverage for Doppler radars is not great because it's only a 100-kilometer radius, and we've got 31 of them. So we've got pockets. We've tried to cover as many population pockets as we can, but we've got lots of areas in between where we've got no coverage at all. Yeah.
So what's going on with the new generation dual polarization Doppler? Are we installing it in Canada? Where are we at? And is that improve your work that you're doing in this area?
Okay, you open up another can of worms now. Okay, so the dual pole, we've got Doppler radar, which measures not only the rain, the precipitation, but also the velocity of that precipitation. Now we've got something called dual polarization radar. And what this does is it shoots out a beam that's oriented vertically, another oriented horizontally, and then the energy that comes back from each of those you can compare. And what that tells you is if you've got more energy in horizontal coming back than the vertical, then you've got a precipitation object that's more shaped like this. And heavy raindrops are shaped like that. It's kind of like a hamburger bun when it's got a big, heavy raindrop. Hail tends to be round and spinning around, and the radar pick it up as round. So that would be 1-to-1. So using those different ratios, we can start to tell what kind of precipitation we're looking at. Is it hail? Is it snow? Is it a bird? Is it a bug? We can tell all these things with this kind of radar. And we can also tell if there's debris in the air from a tornado. There's a tornado debris signature now that we've figured out, and they've been using it in the States quite a bit as well. So that's going to be really useful in the future. Right now, we've got 2 radars that have that capability, one at McGill in Montreal, and then our King radar here in the Toronto area. But the technology is going to be installed across the country at each of the 31 radars. It was supposed to be started already, but we've got a lot of money that's been given to us from the government to do this, so probably within the next 5-10 years it'll all be completed. In the States, they're just about finished installing all of the dual pole capability across the country. So this is another step forward in radar with probably an order of magnitude more data coming from the radar now than before. Okay, how does American Canada provide tornado alerts? So I'm going to show you a couple examples, recent examples, of a tornado scenario. And one is the supercell scenario, the Goshen tornado. The other is a non-supercell tornado, which was that Shelburne EF1. It was the first EF scale rated tornado in Canada. So I'll try to illustrate the Environment Canada's watch and warning process and inherent difficulties. I could do a whole hour and a half talk on this, so I've kind of brought it down to a manageable size. Okay, so let's talk about Goderich first. How many people have heard about the Goderich tornado, and everybody's mostly familiar with it? Okay. So this is a tornado that formed over the lake, and you can see the tornado buried in the rain here over the lake and moving towards the salt mine that was at the edge of Goderich here. This was the before picture of the downtown square. The tornado actually moved through the center of the center of Goderich, hit the downtown square dead on, and pretty much destroyed it. And that's that building there is this building here. So this is what it looked like on the ground after the tornado moved through. This minivan had a family of 4 inside. It was rolled down the street, and they walked away without a scratch. So somehow in Canada we get really lucky with these things. It could always be so much worse.
Wear your seatbelt.
Yeah, wear your seatbelt for sure. Okay, here's the results of the damage survey we did. And so it came onshore, more than 1.5 kilometers wide, and then quickly got narrower. And you can see the track went inland quite a bit. It's a 20-kilometer path round. The path width through this area is 1.5 kilometers. This is a really wide tornado. And it was F3 on the Fujita scale. One fatality, 37 injuries, $150 million cost as it went straight through downtown Goderich, with the worst damage being right in the downtown area. So here's what the radar looked like. Anybody recognize that shape? The hook. That's right. So here's our big supercell storm with the light rain off to the northeast, and then the heavy rain and hail, and then because of the rotation of the storm, this hook wrapping around in here. This is Goderich right here.
Now, could you see this radar signature as it was happening?
Yes.
Or did it take a couple hours to process this image?
Within 10 minutes, you see it. If they didn't see it, they wouldn't have been able to issue anything. Right? This is why we have the radars, to be able to see these kinds of things. The forecaster says, "Holy cow, look at that! Time to issue." So here's Goderich right here. Now, one of the big problems with this storm was that usually when a supercell arrives, you get the light precip first, then heavier precip, and hail, then the tornado. In this case, this whole thing was moving this way. And instead of going through all that first, they got the tornado right away. They got a little bit of hail first, and then bang, got the tornado. Very little warning from the storm itself. That's fairly unusual. So this is what the precipitation scan looked like. Here's what the forecasters deal with when it's looking at the velocity. Pretty noisy. These warm colors are saying that the wind is going away from the radar, and these colors are saying the wind is going towards the radar. And you have to use that to say, oh, okay, that means this area is rotating. So that's kind of a large area of rotation associated with a thunderstorm, and that's what causes that precipitation to wrap around and cause the hook to form. But you can see how noisy that is. It's not easy to interpret. There are algorithms that will say, oh, well, here's an area of rotation, but there's a lot of false alarms. So the forecaster has to say, okay, there's a whole bunch of these things. Which one of these is real? And look at this and say, okay, I think we've got something here.
I presume what's going on varies quite a difference by elevation.
Yeah.
What are we actually looking at? How far
above? Okay, so this is the lowest scan, 0.5 degrees. So it's scanning 1.5 degrees above the horizon, but the radar beam bends. And we're probably looking at about 1.5 kilometers above ground at this point here. Okay, so that's the large scale rotation. Now, I also told you about that tornado vortex signature. That's a precursor to tornado development. Well, this is it here. Again, really hard to see, but there's very tight circulation right in here, embedded in that larger rotation with the storm. And that's what it looks like, again, with the precipitation. So you got a larger area of rotation that's wrapping around, and causing the precipitation to wrap around the back, so that's hook echo, and you can see the warm, moist air coming in here and cutting in this way, and then the tornado is occurring right in here at the center of that hook. If we had that really high-resolution mobile Doppler data that I showed you from Vortex, probably see a nice eye in the middle of that as well. Can't see that with it. We only see something that classic in shape and in strength very, very infrequently. So when a forecaster sees this, they say, whoa, you know, it's all hands on deck. Let's take care of this. And this is what happened with this. I mean, this is a thunderstorm that was very unusual in that it developed over the lake. We rarely ever see that. Usually the lake shuts down a thunderstorm. It happened behind a cold front. Usually all the action happens ahead of the cold front. So there's a lot of things where the forecaster wasn't really looking in this area. But we had one of our more experienced forecasters on, and he saw this at the corner of his eye and said, whoa, hang on a sec, stop everything over there, look at this.
Where is the software that picked that up? Where is it?
Exeter. So it's northwest of London.
Yeah.
Okay, so why did this form over the water like it did? It might be hard to see, but here is southern Ontario, Goderich is here, and this is Michigan. So this is Lake Huron over here. The white line is the storm track. So it actually developed over the water and moved straight, pretty much straight, right into the Goderich area. What these other lines are we had a bunch of earlier showers and thunderstorms that were off to the north. And as they proceeded, a lot of cold air came out of the thunderstorms, like I explained before, and formed an outflow boundary. And that's what this red line is here. So as these storms are going across, this outflow boundary is going out ahead of it, and it's separating the cool air from the thunderstorm from the warm, moist air coming into the thunderstorm. And I mentioned about supercells forming on boundaries, that was the unexpected result of that vortex experiment. And that's what's happened here. You've got this boundary that was across the lakes, and the storm formed on that boundary and just followed it all the way into Goderich. And that's how it was able to develop over the lake. Because usually, if there's not a boundary present, a storm going over the lake, it'll just dissipate because there's not any warm, moist air for it there anymore. So that was quite unusual. So again, occurred well behind the cold front. It developed over Lake Huron, all very rare. Widely used tornado prediction parameters suggested little chance of a significant supercell tornado. Down in the U.S., they've developed these nice parameters where they can pretty much tell now anytime that, well, these numbers are coming up, it's going to be a big tornado day, and they can see this coming days in advance even. In our case, it's a lot more complicated. We get these events that can produce an F3 tornado, and there's no signal. There's nothing that told us that was going to be that kind of a day. The tornado climatology in that area shows a really low frequency of tornadoes in the Goderich area, and really infrequent for F3 plus in general in Ontario. So it was a really rare event. And this is the graphic I was telling you about before that's going to convince you about this corridor of tornadoes. So here are all the tornadoes in Ontario, 1792 to 2009. So we've got quite a large number of tornadoes here. And you can see all of the big tornadoes, the F4s in red, are all in this corridor. Now that's between the lake breeze fronts we usually see and the southwesterly flow, which is kind of our storm environment. So in a southwesterly flow, the cool, moist air from over the lake ends up over land, and in those areas, it pretty much shuts down the thunderstorm activity. You can see in Goderich here, there's only been a couple tornadoes since 1792 in that area, and they were just weak tornadoes at zero. So that air coming off the lake really shuts it down. But these lake breeze fronts extend well inland, and they define this corridor where thunderstorms are going to happen, but can also help to enhance them and actually cause the development of a tornado. So this is stuff we've been working on for 15 years now, trying to show this relationship. And as we go on, it just gets clearer and clearer. Convinced or no?
Well, I don't see the London being protected there at all.
Well, London's down here.
That bullseye that you had.
So it's just on this area here. So a lot of the storm track is just to north of London, getting into Lucan Stratford and all those areas, they tend to see the big tornadoes. Just south of that, they're getting into this lake air. And you can see just south of London, there's been nothing. It's just shut down by the lake. But again, then you get something like Goderich happening where, sure, it's never happened before, but if the right ingredients come together, anything goes, right? You just happen to get a boundary aligned the right way, and who cares about climatology? This is where it's happening.
What's that red dot way up there? I go down there,
Yeah, that kind of stands out, doesn't it? But again, it's in the tornado-prone area, right? I mean, you can get, this is an F4, right? You can get tornadoes that strong out there, even up through here. Yeah.
I think, Paul, just with Taylor, it's kind of different from your bold line map earlier, because there's one bold line just north of Toronto, and then the other one in the Windsor area, but you have a whole bunch of stuff sort of in between those two bold lines. What I'm saying. Well, yeah, I think it's misleading because the bullseyes the things get bigger as they get stronger, right? So it's making it look like there's a lot going on here. But the most tornado activity is in here, in terms of tornadoes, it's independent of their strength. That's where things are happening the most. You can see down through here in Windsor, there's quite a bit of activity through there, Sarnia. But there is this corridor. That's the main idea. Okay, and I wanted to show another thing that forecasters rely on is the computer models that tell us, what the guidance is as far as what they think thunderstorms, where they think thunderstorms are going to occur. And this is on that day of the Goderich tornado, and it shows a lot of thunderstorm activity out in front of that cold front, and then a bunch of little showers out back here. Not much of a signal for the forecaster to say, oh, this is where an F3 tornado is going to be today. It just isn't there. And this is the high-resolution model, the experimental high-resolution model. So it's supposed to be giving even greater details for the forecaster. So in this case, the tornado began to impact Goderich at 3:55. They did have a watch out at 2:02. It included the line that tornado was possible. That's kind of a cover-your-ass statement, though, most of the time. But the lead time was 2 hours. They had a watch out for 2 hours before this happened. The warning was issued at 3:48, and it started affecting Goderich at 3:55. So lead time was 7 minutes there. So we try to aim for maybe 10 minutes. I mean, that's pretty much standard in the States and Canada. It's 10, 15 minutes that you're aiming for that. 7 minutes is not bad. Farther along the track, it was 10 minutes to 15 minutes. Just right where it started, it was only about 7 minutes. And it might have even been sooner, but a marine warning had to be issued first over the lake, for the boaters in the lake, and that took some time, and then they got to the public warning. So anyway, despite this being a really rare situation, the forecasters managed to catch it, provided some lead time, and but who heard the message? There was a book written on this event, Not Like Any Other Sunday, it was called, and they interviewed a whole bunch of people, and hardly anybody had heard a watch 4 warning. They were off playing golf, they were having a family outing, it was Sunday, so they weren't paying attention to the media. Plus, if you listen to a radio station on the weekend, a lot of time it's just robo-programming, right? They don't even have a real person in the office to announce this kind of thing. So, you go to all this trouble to issue this warning, you got the lead time, and here's the message? Not too many people. And it's, that's part of the whole chain from gathering data to the user takes action. That's not very well developed at the moment, is that chain the piece of the chain from the warning goes out to someone takes action. And we're thinking an awful lot about that now, where we hadn't before. We thought Environment Canada before would say, well, we've issued our warning, and that's what we do. But now we're thinking a lot more about, okay, what happens after that warning? Who are our partners? Is the language right? Are people understanding what the content is? And there's a lot of work going on the kind of the social science aspect of the warning now because of this. You can put all the effort you want into a warning, but if no one hears it, what use is it, right? Okay, I don't know what I'm doing for time-wise here. Not so good. It's going long. Do I have enough time to do this, or Yeah, okay. So this is the second example is a non-supercell tornado. And this is part of the leading edge of a small bow echo that was in a squall line. I'll show you that in a minute. And it was rain rats. You couldn't see it. People who were right next to it, storm chasers that I know, didn't even know it was there until the debris came right over their car. 10-kilometer track. The main damage was to a barn near the end of the track. And so that's what we're looking at. It was buried in there. And so the strongest echoes are these red ones here, the leading edge. And these circles here are the rotation detections that I told you about before, the rotation algorithm. So you can see that the algorithm is trying to say, well, there's something going on here and here and here. And so what does the forecaster do? They have to know which ones of those are right and which ones aren't. In this case, when it's not a supercell, it usually is a false detection. This pink arrow here is where the tornado actually was. And here's the start of a little bow, kind of embedded in this line. And if you go to the next time frame here, that's the bow right there. So it occurred right on the front edge of that bow. And looking at the velocity data from the Doppler, there's just a little signature here. We've got this little rotation signature right there, and it survives through here. And that's the only indication you've got that anything's going on there. So pretty tough for the forecaster. And looking at, again, the high-resolution numerical weather prediction model, what's it showing for the area at that time? Not much help at all. It actually had that big squall way back here at that time, so the timing was way off. So, just to summarize for this case, you've got the tornado causing the first damage at 5:33. There was a watch issued way before that, 12:11, so more than 5 hours lead time. They mentioned large hail and damaging winds, but nothing about tornadoes. There was a warning issued at 5:37, so it's actually after the tornado event. I guess it was 1 minute lead time for that barn, because it took a while for the tornado to go along that track. But what was in the warning was most of these storms are not severe. 1 or 2 might produce wind gusts of 90 kilometers an hour and large hail. No mention of a tornado. At the same time, they had a snowfall warning out, freezing rain warning out, rainfall warnings out. So there's a lot going on in the office. And it's hard to, drill down and see if you can find a little tiny rotation signature in there. So the warnings for these bow echo tornadoes are very difficult, like a needle in a haystack, trying to figure out where along that line there could possibly be a tornado. And it's even worse for the Landspout tornadoes, because you've got these kind of big storms going up on a day with not a lot of shear, and any one of them might produce something. You don't know what's going on underneath, how our boundaries are interacting, and might produce that vertical vortex. Very, very difficult. Tend not to get tornado warnings at all for those.
What time of the year was that?
This is in April.
We're talking about snowfall on it? Okay.
Yeah, they cover, the forecasters, there's 2 severe weather forecasters on during the day, and they're covering all of Ontario, northern Ontario, southern Ontario, more than 1 million square kilometers. Have to look at something like 20 radars. There's 20 radars that are in and around Ontario to look at. So there's a lot to do. In the States, just for comparison, every radar has a weather office. So they can spend more time looking at the fine details of this stuff. We're much more reliant on algorithms to try to kind of flag an area, and then we have to spend a little bit of time trying to figure out if it's right or not. But you can imagine the workload. It's just a lot of times it's not possible. Okay, and we are working on improving this situation. I've got a group that's working on this interactive convective analysis and storm tracking prototype. We're trying to optimize the human-machine mix, so what the forecaster brings in as far as pattern recognition skills and judgment skills, and kind of getting that working as best as possible with all of the automation and the numerical guidance we get. So we're working on a new approach to severe thunderstorm nowcasting and alerting, where we get tracks automatically produced from the radar, from satellite, from lightning, and then the forecaster basically is managing those tracks, changing them when necessary, changing the intensity of the storm along that track when necessary. The benefit of this is that you can get first guess warning areas that come out of all this work. And I'll just go over this. When you get that first guess warning area that's automatically produced, the forecaster can change it to to what they think fits best. But the power of this is that all the information that goes into the warning, everything in red, can be pulled out just from this area. So it knows the time of day, of course, what regions we're looking at, what kind of weather we're expecting, whether the track is southeast at 40, and where it's going to be at the end of the track at 8:05 p.m. So a lot of the information can be pulled out automatically from just that work that the forecaster does on the track itself. And another big benefit is that it's done in English and in French at the same time. So a lot of the details can be done bilingually. Right now, the way things are done is everything has to be translated in Ottawa before the full warning goes out. So that can lead to long delays. Sometimes the warning never gets out in both languages, the full warning. It's a very busy day across the country because you've got all these translators that are trying to work on all these warnings. So we're trying to go towards a system where the translation is all done automatically and as much detail as possible gets in. And this is one way to do it. And you can also include probabilistic information such as some clients will be interested in a yes, no. Is it a warning or not? Others want to know, well, is there a 20% chance I'm going to get a severe thunderstorm in my area? And they'll be able to use that information. This is the kind of thing we want to move towards. Okay, final question. Are tornadoes increasing in frequency and intensity? We don't know. And we likely won't know for a long time because, particularly with tornadoes, we've got a low sample size because these are rare events. There's numerous artifacts in the data. As I said, the older data, some of the tornadoes in there probably were downbursts. Some of the data reporting and collection of data depend on EC resources at the time. So in the mid-'80s, things were pretty tight. No one went out and did damage surveys for like 2 years. And then resources came back up and we're out in the field all the time. So that really changes the numbers from year to year. The rise of commercial electronics. We're getting tons of people sending in photos now, whereas before it just wasn't happening. Even in remote areas, because there's a lot of tourist and fishing villages in northern Ontario and that kind of thing. Suddenly we're getting data from some of those places because of cell phones and cheap cameras. Storm chasers, as I mentioned, I've got a friend who saw 4 tornadoes. He's a storm chaser out of Fergus. He saw 4 tornadoes last summer in Ontario, which is unheard of. A lot of them, if he hadn't seen them, they wouldn't have made the database. They're just weak and in the middle of nowhere. So all these things add to different biases in the data set that are really difficult to pull out, disentangle. But I will give you this. Here's a plot of 2 things. This is the annual number of tornadoes in red and the number of tornado days in blue. Tornado days being, doesn't matter how many tornadoes occurred on that day, it's just one tornado day. This is 1980 on, pre-1980. So you can see before 1980, the quality probably, this is back to 1970. You can see there's quite a bit of change between 1970 and 1980. And that's likely due just to the number of reports received and the quality of data rather than anything to do with tornadoes itself. But we're pretty confident in this 80 onward. Again, there are still some artifacts in there, but we're much more confident than we are pre-1980. And what are we seeing? Year to year, quite a bit of noise. Some years, like last year in Ontario, we got 23 tornadoes, when the average is about 12. Other years, we get far below that. It depends on what kind of weather regime sets up that summer. But you can see this number is fairly steady, though, this tornado days. And hasn't changed all that much in a 30-year time span. Again, it's a kind of a low sample size, 30 years. It probably will take 100 years before we start seeing a signal we can actually believe, and maybe 200 years before we can say, oh, there it is. And by that time, won't be much use to you. But like I said, this kind of gives you the hint that not much is changing drastically in the last 30 years. Okay, and there's a lot of people who helped prepare material for this presentation over the years, and lots of references if you're interested in following up on anything. And that's it. Thanks.
Questions?
several of us jump in along the way. I think we use that question, I think. Let's see what the question. Glenn?
I think you kind of said at the beginning that there's still a lot we don't know about the creation of supercells and why we get F4s and F5s. So they're pretty rare, but there's still a big gap there. I think there's also a big gap in understanding outbreaks and what triggers outbreaks. And I think, there's any progress in the research on either of those two things?
Well, I mean, that was one of the goals of Vortex 2, if you've got two supercells that look very similar on radar, why does one produce a tornado and it gets into some of the really small scale details of the storm itself. Like I mentioned, the downdraft air that comes out of the thunderstorm, they found that the temperature of that air makes a big difference to whether a tornado develops or not. If it's too cold, too stable, the air won't be able to be lifted into the tornado, and the tornado just doesn't form. And you can measure that kind of thing when you've got a whole bunch of instrumentation around a thunderstorm. So how do you know that in a real-time situation at the forecast office? You don't have that kind of data. So, I mean, we're looking for proxies for that, something that we do measure that can kind of point out that might be the case, but no smoking guns yet. And it's hard to see where there will be. It just stuff happens on such a small scale that can have the large impact on the storm itself. And the model, the Americans are, their aim is to have thunderstorm warnings done by the numerical models. So they want to be able to model a supercell thunderstorm. It'll produce a tornado in the model ahead of time, give 30 minutes to an hour lead time, and say, the model is saying it's producing a tornadic thunderstorm, and we're going to put out the warning. And you can see from the examples I showed that the high-res modeling is often just not there for these high-impact cases. So I don't know. They say within 20 years they'll be able to do it, but I've got serious doubt that that's the case.
You get the opportunity to collaborate much with your American counterparts, or are you guys running parallel streams?
Well, it depends on what in particular, but I'm working with them on the EF scale, the changes to that. I've got some close colleagues for the tornado climatology, the Harold Brooks and Chuck Doswell that I've been working with. And with the nowcasting and forecasting system that we're coming up with, we have collaborations all over the world that people are working on similar stuff. We're the only ones that are working on kind of trying to inject that human component back into it. A lot of people are way more focused on trying to automate it completely. And we've taken the approach that, well, to see that this is not going to be something that's achievable within 10, 20 years. So let's use the resources we have in the best way possible, and that's what we're aiming for. But yeah, we collaborate quite closely with a lot of our colleagues, especially in the States. And obviously with the Vortex program, we were down there as well. We're the only international contingent that was out there taking the measurements.
Okay. And I'm going to close things. Okay, sure. Okay, so I'm going to close. Could everybody please join me in thanking Dave? These are really complicated issues. If you've ever tried to read